So today we're going to do what are called cylindrical coordinates. Now cylindrical coordinates are actually one of the simpler concepts because they're basically polar coordinates in 3D. So there's not a whole lot of difference. But the main difference is with polar coordinates, okay, this is a rectangular integral. We've been doing this now for a couple of weeks. We're pretty comfortable. Our region, let's say, is circular, or our integrand involves x squared plus y squareds, maybe in a denominator, maybe under a square root, but in some capacity that I cannot do any form of, substitution, and more likely a little bit of both, circular regions. So I'm going to go ahead and switch this to polar. So I do the integral, and I'm going to write it this way, f of r comma theta, because I just simply replace everything x and y-ish with things that are r and theta-ish, right? X is r cos theta, y is r sine theta, and if I have an x squared plus y squared, I just go straight to the r squared. And then what? R dr d theta. And we're very comfortable with that, that's great. What if I need a triple integral though? So why would I need a triple integral? What if I give you a density that's a function of x, y, and z? That'd be a simple example. Or what if my boundaries, again, I have a three-dimensional solid, but my boundaries involve polar in some way? Well, then what we do is we do a triple integral. And in the triple integral, excuse me, and this thing here, now I need to do the following substitution. X is r cos theta. Y is r sine theta. This sounds vaguely familiar, doesn't it? And this is the one you're never going to see coming. Z, just stay at Z. You're going to do a triple integral where you don't do anything with the Z. Because Z isn't the polar part. The polar is the part in the xy plane. The region in the xy plane is circular in nature, so you need to mess with it. What you cannot do is start a problem rectangularly and then halfway through, now let me switch it to polar, because you've got x, y's, and z's in your integrand. And some of you ran into this problem on the last quiz. You had integrals where you changed part of it to polar. So I saw a lot of integrals where there was an x, a y, an r, and a theta all in the same integral at the same time. That's actually impossible. Remember, a dependent and an independent variable cannot simultaneously exist. So if r is a function of theta, but the transformation from x and y, yeah, it's one or the other. I do a complete swap out at the same time. So I have this situation here. The polar part is exactly the same. The part in the xy plane is the same, and then the z just stays z. So let's do a simple example of this. And I'm going to do a simple volume problem. And I'm going to show you how easy this is to do. Because if I throw in a density and make it a mass problem, it doesn't become more complicated. I just have an additional thing in my integrand. So let's say that we have z equals 36 minus x squared minus y squared, and z equals 0. And I want to find the volume bound by this thing here. Well, if I start with my floor and ceiling being the z's, you cannot have a rectangular integral with x, y, z, r, and theta at the same time. It's one or the other. So we'd say, you know what? Let's make this cylindrical. Now, the reason it's called cylindrical coordinates is polar coordinates really involve circles. We know that. But circles are two-dimensional. If I think of a circular cylinder, a circular cylinder is sort of like a three-dimensional circle. It's the circle, remember, that I've extended it. Because we talked about cylindrical shapes. So a circular cylinder is a lot like a circle in terms of the geometry and how I calculate things. And the nice thing is, because it's straight, right? So a circular cylinder. Don't confuse that with a sphere. We're going to do that the second part of class today. That one's a bit more complicated. So I want to set this problem up. So one of the first things I'm going to do is I'm going to look at my ceiling, and how should I rewrite that ceiling? So right now I'm doing a volume problem, so it's simply dV, because I don't have an integrand yet. But when I switch this to polar, technically this portion here is still the region in the xy plane, isn't it? And this portion here is the z-ish. Now, I don't have to make floor and ceiling the z. I could go sideways, I could go this way. But because of the shape that I gave you, it's very obvious that floor and ceiling are the z's, not any other variable. That makes it a little easier. So I'm going to integrate with respect to z first, and then do the region in the xy plane, which of course in this case would be polar region. Agreed? What is the region in the xy plane? So when I'm standing on top of the z-axis and I'm looking down, what do I see?
Circle.
I see this circle. What is that circle exactly?
X versus y squared equals 36.
Now how did you get that? Because when z is 0, then it's x. Oh, okay. It's actually that simple. There's no algebra to perform here. So this is my region in the xy plane, which is obviously a circle of radius 6. So when I convert this to cylindrical, my theta is going to go from 0 to 2 pi. My r is going to go from 0 to 6. And what is z going to range from? Like this, right? And my little parallelepiped right there. Z is going to range from z equals 0 to what? Which is exactly what? 36 minus r squared. Perfect. Do you see this is 36 minus the sum of x squared plus y squared? Which means in polar world it's 36 minus r squared. You cannot put x and y in your limits of integration when x and y are no longer variables in the problem. Does that sound cool? Now, what goes here? R. Just like before, dz, dr, d theta. This is the major difference. Oh, okay. Well, that's not really that complicated, is it? Now, some people like to put the r here. No, these are instructions. These are not quantities. You can't manipulate things and put them on the other side of an instruction. That'd basically be the same as factoring it out of the entire problem. People will do that and say, well, it still works. No, it doesn't. These are completely separate from the problem. They're outside the problem. You can't just like arbitrarily, let me throw some variables in here and here while I'm at it. No. It doesn't work that way, but I got the right answer that time. In general, that doesn't work. So I'm going to integrate with respect to z. That's still the biggest problem that we have, is forgetting this. If I forget this, it changes the answer significantly, obviously. So when I integrate this, what do I get? 0 to 2 pi, 0 to 6, rz from 0 to 36 minus r squared, dr, d theta. Now, could I change the order of integration? Would that be possible? Could I have integrated r of theta before z? When can you easily change the order of integration? Tell me. When the limits of integration are all constant. But see my z limits? They're not constant. So if I switch the order of integration, that would make it way more complicated because r would no longer be constant. R would have to go from something to z, something z-ish. That would be very complicated to try to switch it. That'd be almost like saying, let me look at it sideways. So this would be the best order I can go, and pretty much it's always going to be this order, dz, dr, d theta. Just the nature of the problems. So when I substitute here, I'm replacing z with this, so that's going to be r times 36 minus r squared dr d theta. Now, there's nothing about this integral that looks scary. So this quantity right here, how about 36r minus r cubed? So I'll go ahead and integrate that. So 18r squared minus 1/4 r cubed from 0 to 6 d theta. Without your calculators, what does that give us? Nice happy number.
I think it's supposed to be 1/4 r
Did I?
to the 4.
Oh, thank you, Kenny. You're right. R to the 4th. Good catch, good catch.
324.
That whole quantity is 324?
That's what I got.
Everybody got that? Well, I love this answer, don't I? I have a constant with constant limits of integration. That one, it's this times the difference, so this one I don't have to integrate. There's a tendency that a lot of times people try to skip the antiderivative step. Never skip the antiderivative because your antiderivative is a function. You only can skip the antiderivative step on the last step if everything is constant, because it isn't going to change anything. Now, that answer is that's the volume. Don't put any meaning to it. That's the volume of my gumdrop there, of my bullet shape. But we were able to find it by using cylindrical coordinates, and it wasn't that complicated. Now, what if I had said, I have the exact same shape, but I'm going to give you a density? What would we do different? In other words, I want the mass of this object. Well, we saw last day, when you're doing the mass, you're still integrating over the volume. If it's two-dimensional, you're still integrating over the area, but you have an additional thing in your integrand, the density. So if I wanted this to be a mass problem, I'm going to change this now to mass. What would be different? I would insert the density right here, and everything else would remain the same. So density, which is now a function of x, y, and z, would go right there. So it means I would have more stuff here. But everything else about the problem, absolutely the same. Okay? Simple? All right, so I promised you we were going to discuss probably the most important problem coming up over the next few weeks. Thanksgiving is right around the corner. You're going to hopefully, this is where I feel bad for vegetarians every year. Just, Thanksgiving is like the most epic meal ever, and my wife makes the most unbelievable. Yeah, we do everything right. She makes her own cranberries, Cuisinart, grind it up. But there are those who will go someplace where they will have the nasty Jell-O salad with the old fruit cocktail at the bottom, and worse, they will pull out the can of cranberries. That thing. I tell people, I'm a pretty brave individual. I'm only afraid of a few things: spiders, clowns, and food that jiggles, and that's not a joke. Food that jiggles terrifies me. Jell-O, things of that nature. That nasty cranberry thing. But the nasty cranberry thing, when you open it up, it's all liquidy at the top. And it's all really thick and sludgy at the bottom, meaning it is not of uniform density. So here's our goal today. This is a very, very important goal because, you may be involved in the serving of this thing, and, you want to be able to explain to the audience, hey, here's where the center of mass of this shape is. I know this. So we're going to calculate the center of mass of the nasty can of cranberries. You with me on that? So let's say the nasty can, let's see, probably about, I'm going to guess about 15 centimeters this way. It never makes it into my house, so I'm not absolutely sure how big it is. And what do you think the radius of that can would probably be? About maybe maybe 6 centimeters? I don't know. Just let's go with those numbers. Okay. Now tell me about the density. What happens to the density of the can of cranberries? Like most canned goods that aren't pure liquid, it gets more or less dense as I go down. More dense. So the density decreases as I go up. So density clearly has an inverse relationship with the height. Okay? Some sort of inverse relationship with the height. So I need to set this problem up. So before I can give you a density function, I actually need axes. So do you want to put your can on its side, or do you want to put your can vertical? You're probably storing it vertically, so that makes more sense. Where do you want to put your XY plane? You want to put it in the middle? Probably at the bottom, because otherwise I have negative coordinates, and that might be a little bit harder to conceptualize. So I'm going to put my y-axis here. I'm showing you in real life you actually can do this, and then to me the most logical thing, if it's not automatically obvious, is have the z-axis running right down the middle. I can put the entire can in the first octant, but then that makes the center of mass somewhere out there, and that's a little bit harder to work with. It's not impossible, but algebraically it's actually way more work. It's kind of like manipulating a circle that's centered at the origin versus manipulating a circle that's centered somewhere else. You have more going on, and it can be a little bit trickier. So If we start with this, then let me define the density. We said it has a reciprocal relationship probably with the height. Now, here's one thing we discussed last day. As you move horizontally, something that has already sat for a while, it's settled. As you move horizontally, will density generally change? No. How do you know that? It's the G word. Gravity. Yeah. Density is what it is. Gravity determined everything else. Okay, based on gravity, that's why more thickness is at the bottom than at the top, because it's weighted. But it's not going like this. It's going horizontally. So if I took a horizontal slice, it's reasonable to say that will have uniform density, that slice. But if I do another horizontal slice, it will have different density than the previous one, but uniform horizontally, not uniform vertically. So let's say our density, we'll keep it simple. I'm just going to make a really simple function. Let's say it's 1 over z plus 1. I can't say 1 over z, because what happens when z is 0? That means your can is infinitely dense at the bottom. Well, you know, it really is that thick, but probably not infinitely dense, so just very dense. Now, I'm just making one up so we have the purposes of doing something. You could probably contact the manufacturer of the can, and they can give you the exact, the exact density function that they use in their calculations when they're putting the cans together. Because you know that's a calculus problem, right? Everybody who makes cranberry cans, they do all the calculus first, I think. Okay, I want to find the center of mass here. That means I have to find the mass and 3 moments. So folks, roll up your sleeves, that's what we're going to do. This is the entire point of last lecture and today's lecture kind of combined into one. So we can do all of these things. So now, how do I describe this thing? Well, I don't want the volume, I want the mass. But the integral for the mass is going to look a heck of a lot like the integral for the volume. Remember? We're just going to insert the density. So if I want the mass, let's start here. You all agree with that? Now, there's nothing about the integrand that troubles me, but because this shape actually is a circular cylinder, I'm pretty sure cylindrical coordinates would make the most sense. That's kind of what it's named after, right? So when I'm setting this up, let's do the easy part. The circle in the xy plane is what circle?
6 equals x squared plus y.
Yeah, but think polar.
R equals 6.
R equals 6. Lest we forget, R equal a constant is a circle of that radius centered at the origin. We worked backwards to show this. X squared plus y squared equals r squared is a circle centered at the origin of radius r. Oh, so if I just said r equals 6, that's the same circle as you're describing, but it's easier because I'm already in polar now. So r is 6, so I'm going from 0 to 6, 0 to 2 pi. What's z doing?
Going up 15 centimeters.
What's the z limits?
0 to 15.
0 to 15. My z limits are constant because it's a circular cylinder. I'm not bounded by another function. Think of it this way. I have a circular cylinder centered on the z-axis of radius 6 that goes forever. It's a circular cylinder that goes forever. I'm cutting it off with the plane z equals 0 and the plane z equals 15. Does that make sense? Oh, okay, so now I just have that section. So the z is going from z equals 0 to z equals 15, not z equals some other function. And then finally, my density, r dz dr d theta. Okay, so let's do this. So you all see it. So my first integration. What is the antiderivative? I'm integrating with respect to z, so technically I can treat r as a constant. What's the antiderivative of 1 over z plus 1?
ln is z plus 1.
Good. Natural log of z plus 1. So this would be ln absolute value z plus 1 r evaluated from 0 to 15 dr d theta. You with me on that? I'm only evaluating the z. R is going along for the right at this point. When I evaluate it at 15, I get what?
RL is 16.
I get log of 16. When I evaluate it at 0, what do I get?
0.
Log of 1, which is 0. Everybody got that? Oh, okay, so what's left? Just log 16 times R. Log 16, think of it as a coefficient. All right. You with me so far? Now let's evaluate this, or integrate this, I should say. That's a constant, so 1/2 R squared. So how about log 16 over 2 R squared? From 0 to 6. And what does that get me?
Log 16.
So 6 squared minus 0 squared. So I'm going to have 0 to 2 pi of, it looks like 18 log 16 d theta, but 18 log 16 is a constant. So can I just go ahead and evaluate this now? Yep. I'm being a little bit tight right here because I'm going to use the whole board and I don't want to erase anything as I go. So my final answer here looks like 36 pi log 16. So I'm going to write that up high. So we just have it. So the mass is 36 pi log 16. Something truly icky. Okay. Now let's find our moments. It doesn't matter what order we do things, so let's do the x distance first, the y distance second, the z distance third. So that means the first moment we're going to find is the moment to the yz plane what goes here?
X.
X. I'm going to do 3 moments. They're all going to look exactly the same. One of them's going to have an X, one of them's going to have a Y, one of them's going to have a Z. I have to understand, if I don't see that, I'm not going to do it correctly. Remember, the moment is everything about the mass multiplied by the distance. So the distance to the YZ plane is the X distance. Now I can convert this to polar. So the limits are really easy, but what else do I have to do? I got to change that guy to what?
R goes up.
R cos. I swallowed a bug. All right, so 0 to 2 pi, 0 to 6, 0 to 15, 1 over z plus 1 r cos theta, yikes, times r dr d theta, or r dz dr d theta. Still can't forget that r. Wow, this one got a lot busier, didn't it? But I'm still doing the z first. Everything else is still treated as a constant, so I'm still going to get the logarithm that I just got a moment ago. So this is going to be log absolute value z plus 1 r squared cos theta, again from 0 to 15 dr d theta. So this isn't the same, but the z portion should be exactly the same because I did not add any z's. When we get to the xy moment, then we're going to multiply by a z. That's the only one where the z part will be different. Okay, so what do I got now? Still log 16, just like before? Okay, I'm integrating with respect to r. Now it's getting a little bit small now. With respect to r, so that would be log 16 over 3 r cubed cos theta from 0 to 6 d theta, and what will that be?
Natural log
So
16.
72 log 16 cos theta. Okay? Hopefully you can see this one. This will be the lowest I go here. Now I'm integrating cos. Interestingly enough, we're a Calc 3 class. That should be trivial. I'm getting a lot of incorrect antiderivatives lately of cosine. If the derivative of sine is cos, then the antiderivative of cos is sine, not negative sine. I'm getting a lot of incorrect. That's not a mistake you can afford to make in general. So what am I going to get? I'm going to get 72 log 16 sine theta from 0 to 2 pi. Wait a minute. From 0 to 2 pi? What's that?
0.
Oh. Little question mark. That's kind of curious. All right. Well. Huh. Who knew? Okay. Let's keep going. I'll be back this time. Let's do the moment to the xz axis. And then what are we going to include?
Y.
Going out of my way to make this, just stand out. It's always going to be like this. Now, this is the longest problem we're ever going to do.
Can we skip this one or we're doing?
No, gotta show it because it's not always. I know what you're thinking. And by the way, and it's important that we, after the fact, can go back and do things. So, what is this going to look like? Well, it's going to look a lot like this one. What's the major difference?
Sine theta.
It's going to be a sine theta, yeah. And this is going to be r sine theta, r dz dr d theta. All right, so we can we can fast forward a little bit of this. Do we know we're going to get to here? Do you all agree? We're going to get to here. So I'm going to just go ahead and skip. Well, I'm only skipping one line, but we know that's what we're going to get because the z, again, did not change. So log 16 r squared sine theta dr d theta. All right, so that's going to be log 16 over 3 r cubed sine theta from 0 to 6. Wow, this is really looking familiar. So that's, again, the same numbers. So 72 log 16 times the sine of theta d theta. Well, this one's going to be a negative, right? So negative 72 log 16 cos theta from 0 to 2 pi, which is what, right? 0. Okay, so all of our moments are going to be 0? That seems really strange. Well, maybe not all of them. And we have one more to find. This is going to be the busiest one of all, probably. No, actually, it'll be the least busy of those three. Now I'm going to insert a z, which makes this one a little bit trickier, or does it?
Should it be a moment of
Oh,
x, y?
what did I say?
Y, z.
Thank you. That should be xy. Thank you. Good catch. Now, that cannot be dealt with. Remember, there's an absolute that you learned as babies in algebra that people forget. You can never do anything in a rational function unless the degree of the numerator is what? Smaller. Period. There's no exception. So you got to do something. Notice that can't be dealt with. There's no calculus you can do that. You wouldn't even want to take a derivative of that. You'd want to change it, long division, synthetic division, or what people affectionately refer to for centuries as Brown division. I don't ever do longer synthetic. I'm way too lazy. I'm way too lazy. every algebraic operation you ever learned in your life can probably be shortened significantly because you never learn things the fast way. These types of problems absolutely should always be done in one step. If you add and subtract to the numerator, that's how you derived your product and quotient rules. You added and subtracted to the numerator and then manipulated it. So regardless of how you do it, that's what you're going to get. I can integrate that. Can't integrate that. Okay? Everybody cool with that? However you get there is fine. I'd just rather you not spend any time. Just get right to it. Now my integrand is 1 minus 1 over z plus 1 r dz dr d theta. Now I can't really fast forward because my integrand is different now. I need to go through the whole process. There's no shortcuts here. I mean, that piece is going to look real familiar, obviously. So now I've got, and by the way, I can leave the r on the outside because this is only z-ish stuff. So it's going to be z minus natural log of z plus 1 from 0 to 15 r dr, r dr d theta. Now, this is going to be exactly the same as it was before. It's still going to be just log 16. But what about that piece? It's going to be 15 minus log 16. Okay? That's just a constant, and by the way, it's positive. 15 is a lot bigger than log 16. I'm integrating with respect to r. So how about 15 minus log 16 all over 2? It's just a constant. 0 to 6 d theta. Not so bad, right? So what have I got now? It looks like I have 18 times 15 minus log 16 d theta. That's just a constant integrand. So what is that going to be? By the way, you can distribute. I think this makes it messy at the moment. But yeah, distributing is absolutely correct. So what am I going to get?
36 pi.
36 pi times 15 minus log 16. If I want to distribute, that's fine. Remember, I'm going to be finding quotients in a moment. So the form do you want to deal with, you can figure it out later. So right now, it looks like, my blue pens are drying up here. Let's hold the blue light rod. What did we say, 36? All right, now I'd like to find my center of mass. I cannot find the center of mass until I have all of these things. Now the center of mass is just going to be 3 quotients where the mass is the denominator of all 3, not the moments. that would be a problem if I tried to make the moments the denominators. So, x bar equals y bar equals 0. So what are we saying? The center of mass is entirely on the z-axis. Is that a shock? Or does that make perfect sense? What did we say? Density does not change horizontally, and if I'm moving outwards in a circle, then if I think of every slice I could take, we'd say the center of that circle should be the center of mass of every slice I could consider. I mean, that's just logical. That's not a calculus concept. So it makes perfect sense that my center of mass ought to be on the z-axis. But we actually had to show it. How come it's on the z-axis? Because my density was independent of x and y. It only involved z. That's part of it. If my density had x or y in it, no, then it would not be on the z-axis. But then that would not have been very realistic either, because we just said horizontally it really shouldn't change. So now what is the z-bar? So it's 36 pi, what did I say, 15 minus log 16 all over. What is, I can't see that far, what is it?
Pi L pi.
It's not that bad. I think I'm gonna start by canceling the 36 pi. What do you think? Probably good one. Now what have I got left? Pull them apart. I have 15 over log 16 minus 1. So it appears that our centroid, our center of mass, our center of gravity, all of those things are correct. Is at 0, 0, what did I just say? 15 over log 16. Is that what it says? I can't, that's too far. 15 over log 16?
-1.
Minus 1. Now, you didn't have to break it up. That's probably easier to read. Now, somebody give me a numerical value for the z-coordinate.
4.41.
4.41. Does anybody agree with that?
Yeah.
This thing is 15 centimeters high, but you're saying my center of gravity is the bottom third? Huh, why is that? Way more dense at the bottom than it is at the top. So does that answer make sense to you now, based on everything? Yeah. Now, real life, I know this about things. Does that help me understand how to transport things if I know where the center of mass of something is? If the center of mass is lower, does that mean it's easier or harder to tip over? Harder. Oh, okay. So I have all these cans, and I accidentally start stacking them upside down. It takes some time, by the way, for the shifting to occur, right? That peanut butter that you want to, reverse, it's going to take several hours, maybe a couple days, before all the oil changes places. So I stack all these cans upside down. Now I've got the center of mass near the top. What am I going to find? Very unstable. Very unstable. And you guys probably all have experienced something of this nature where, things tip over really, really easily. You go, wow, I don't like that. It's the tipping over part. Any question on any part of this? So this is combining center of mass, which we did last day, which is always a triple integral, with cylindrical coordinates. So in general, again, if your integrand or your region, and it's always going to be the XY plane, if they suggest a polar switch, then you're going to use cylindrical because of what you're finding. Remember, you set up the problem any way you want. I gave you a can. When you go to the store, I checked. I just was at the store yesterday. I'm at the store all the time. I could not find the X, Y, and Z axes anywhere at the store. I looked, I thought they'd certainly be in the shelves, going through the cans, and they weren't there. So you got to put them wherever you want them. You got to put them whatever makes it convenient for you guys. And literally, we chose this orientation. Could we have done a different orientation? Absolutely. But the problem with a different orientation, it would have made the setup probably a bit more complicated and maybe less logical. So that's why I like this setup, because it was less likely to mess up. Having the z-axis go through the middle of the can just seems logical. Didn't have to do it that way. But if I don't have the z-axis going through the middle of the can, then my circle's not centered at the origin in the xy plane, which means I now have a different equation of the circle, which is actually much more complicated. And my limits of integration, neither one of these would be true anymore. I'd be going from 0 to function, and it definitely wouldn't be 0 to 2 pi. It'd probably be 0 to pi, as we've seen. Oh, gosh. So we chose this because it's convenient. So cylindrical is just polar in 3D. You're not doing anything different in your integration. You're just doing a triple integral. Now I'm going to go to the most complicated one of all. The next one we're going to look at is called, oops, some of you have looked ahead, maybe watched a video or looked at the notes. We're going to do something called spherical coordinates. That means obviously a sphere is going to be somehow central to this, excuse me, this process. I'm going to give you a simple application problem that we're going to do in a little while. And I'm going to give you the question first, and then we'll come back and attack the question after we do all of our setup. Maybe here's what I want to do. That's the center of the sphere. That's a cone shape, except it's got the dome on top. Or the circular cone would be flat on top. So think of this as the ice cream cone with the ice cream on top. Everybody got it? So I've got the ice cream on top of the ice cream cone. I'd like to know that volume. We can set this up using cylindrical coordinates. Man, it would be a bear. Trust me, that would be a really complicated and a very difficult integration. We could all do it. But think about it, you gotta make your slices so you're going from here to surface, and then, yeah, it gets really, really nasty. We're gonna do this problem in a few minutes using spherical coordinates, and we're gonna find it's absolutely a piece of cake, because I'm gonna use the fact that I'm bounded by a sphere originally. I'm gonna use that to my advantage. So spherical coordinates, one of two things. Either your region, literally in 3D, is bounded somehow by a sphere, or your integrand itself looks spherical, not circular. Remember, a sphere would be x squared plus y squared plus z squared equals a constant. So, all right. Made myself some pretty pictures. I like to be consistent. Sorry. My pens. My glue is dying on me, so I may have to go to orange for a minute. By the way, does anybody here have difficulty seeing the orange? Nobody? Because I know somebody in my next class always reminds me they literally can't see the orange when I put it up there, which I think is, you know, a strange form of color blindness, I guess. That the orange is the only one that. So I have to ask, because if I'm doing things and you can't see it, then well, that might be a problem. So I have a point, x, y, z. Okay, great. So what I want to do first of all is project this. Project it here. And I'm going to project it down onto the xy plane. Now, what would that point be? I'm projecting it straight down to the xy plane, so that would now be x comma y comma 0. Okay? This I'm going straight across, so that point would be, what would that point be?
0, 0, z.
Good. That means I have a right angle here, I have a right angle here. It's coming out at you. So I have a point here in free space. First thing I want to do is go straight across back to the z-axis. I want to go straight down to the xy plane, and then I want to go back to the z-axis. That means that this would be r. Because that's on the xy plane. Okay, everybody cool with that? That's the y-axis, that's the x-axis, so that angle there would be theta. As that's what theta is, the angle between the x-axis and the r. Okay, great. Well, that's not very complicated. These are kind of supposed to be parallel. Pretend they are. Now, I have that line segment. If I said, I want you to construct the sphere, where this is the radius, then my sphere would travel through this point and center at the origin. Then we would call this distance rho. That's what rho always represents, the radius of the sphere. Whether it's through the origin or not, it's not important. That's the radius of the sphere. So I'm going from the origin out to my point. That distance is rho. Rho is not r. Rho is longer than r, isn't it? In fact, there's going to be a SOHCAHTOA relationship there, isn't there? Now, I'm coming out here. Let me grab my prop here. On the floor, if this is on the floor, that's the x-axis. Theta is the angle made between this here. Okay? That's what theta is. I'll put it up here. This is theta. Now my point's coming out into 3 space. There's an angle between the z and the rho. That has absolutely nothing to do with theta, because as I move this way and I move that way, theta changes. But this angle, it wouldn't change. This angle is called phi. Now this is the part of the course that people have to really be careful on, because a lot of us are very lazy when we make our thetas, myself included. Theta has a horizontal, phi has a vertical. And what do most of us do? some diagonal that's right in between them, because there was never, any possibility of ambiguity. Now there will always be a possibility, because you will never use phi without also be using theta at the exact same time. In other words, they always show up as a pair. So now I must caution you, be very, very careful in how you make your thetas and your phis. So phi is vertical, theta is horizontal. Phi is the angle made between rho and the z-axis. Again, theta is the same theta from polar. That didn't change. But they're completely unrelated to each other, because theta lives on the xy plane. Okay? Now, with this, I would like to change x, y, and z into things involving rho, theta, and phi. Whoa. That sounds kind of crazy, doesn't it? Well, what do we know? Here's what we absolutely know. X squared plus y squared plus z squared equals rho squared. Agreed? We know that. It's a terrible law. Okay. But wait a minute, what does x squared plus y squared equal? Doesn't that equal r squared? So then wouldn't this also be a true statement? So look here. That's z. Do you agree? That length is z. What's that length?
R.
That's r. Oh, clearly I have a right triangle relationship there between z, r, and rho. And that's where it is. Rho would be the hypotenuse of that right triangle. Everybody cool with that? And the right angle is between the r and the z. Okay, cool. That seems consistent. All right? Now, what else do I know? Well, I also know from my picture. All right, now, look at this right here. Look at that triangle there. Not the z. Look at the r, the phi, and the rho. There's a so-ka-tor relationship there. What is it? Is it so, ka, or toa? So, right, that's opposite. Okay, so there's a so relationship. In fact, what is the sign of phi? It would be r over rho. Therefore, what does r equal? Rho sine phi. Because you just said there's the so-ka-tor relationship there is that sine of phi is r over rho. Okay, that's not really in question. Okay, now there's a so-ka-tor relationship between z, phi, and r. Is that so, ka, or toa? It can't be so, because that's the other. It's got to be the ka, right? Because that's adjacent now. Okay, so what is that relationship between those two? That would be z equals rho cosine phi. Now, finally, if r equals rho sine phi and z equals rho cosine phi, how do I get the x part? I mean, how do I manipulate that? Okay. Well, in polar, isn't this what x is? That's not in question. We know that. Ooh, I'm going to replace r with rho sine phi. Cool. Everybody see that? How about y? Doesn't y equal r sine theta on the xy plane? Yep. So if I replace r, and we now have our spherical transformation. I replace z with rho cos phi. I replace x with rho sine phi cos theta. I replace y with rho sine phi sine theta. You notice the z doesn't have any thetas in it, because z being straight up and down isn't affected by the polar part. It's only affected by the phi. Everybody cool with that? So if I had an integrand involving x, y's, and z's, this is how I would swap them out. And often your integrand is going to involve x squared plus y squared plus z squared in some capacity. All right, now, we did a geometric conversion in polar where I actually found the area of the little slices and we realized we had to insert the R. R wasn't because I told you it was there. It was a geometric thing. We found an actual area. We're going to do something similar. I'm going to do my best. It is really hard for me to do this one because I'm going to draw a three-dimensional coring of a sphere. And I do a terrible job of this every time. And in the textbooks, I look at the textbooks and there it's even worse. Too many dotted lines and they're showing things. But I'm going to set it up on, let me double check. I think it's next class, actually. Next class. Yep, next class, we actually do a calculus derivation of the R in the RDRD theta. We do it from a completely different point of view. Those in linear, this is where we actually use linear algebra. We actually use matrices and stuff to show how that works. It's kind of cool. And I'm going to do the same thing for what I'm going to do now. I'm going to derive it a completely unrelated way. Nothing to do with the geometry. It's a very cool thing, okay? But right now I'm going to do my best to draw a picture. In my sphere, if I took a core and then I kind of sliced this up, I'm gonna do the best to show what it looks like. Okay, like I said, this is in every textbook, but it is really hard to interpret sometimes. Sorry, get rid of some of this stuff. You don't need to know exactly why, but I want you to see where something came from. I don't want to just tell you a result. I hate doing that. If I do, oh, by the way, here, do it this way, and then I forget something. You know, if we did polar and I never derived the whole thing, I forgot about the R and the RDRD theta, we'd be doing everything wrong, and, well, I never showed you where it came from anyway, so we wouldn't know we were doing it wrong. But I showed you where it came from, so now we know. All right, let me get the black one. My pens are disappearing. Here we go. So, this thing, I'm going to kind of do my best. I know this is kind of sad and pathetic, but okay. It's not a rectangular prism, right? But do you remember when we did it with the circle and we did the slices? If I make the delta R small enough and the delta theta small enough, it was essentially rectangular. We kind of use that a little bit. This is kind of almost prism. If I make things small enough, I can say loosely, I can multiply the three dimensions together to tell you what the volume of that piece is. That's what I'm saying, it's very loose. But we understand it because there's a limiting process that comes up. Now, this from here to here is clearly the delta. I'll call that, let's see, what do I, J, and K. I want to do that one. I'll do this phi I because the slices are independent job. I have an I, a J, and a K slice. And again, don't worry about drawing this. If you have access to a book, it's easier to see. So that piece right there, that's delta phi J, okay, because of, you know, that angle change. And then when I project, I'm going to project this part straight down. And that width will be delta theta ijk. Okay? So far so good? Now, reminder, this is something we know, but I pull this out every now and then. The three equal ratios that come whenever I take the sector of the circle. The sector, because that's coming from the central angle. Sorry. So we know that theta is to 2 pi as the area is to pi r squared, as s is to 2 pi r. We know this is true. And we get a lot of our really important formulas in calculus even from that. In Calc 2, that's where we got our polar integrals from. So if I put those two together, okay, the one I want to use, I want to put these two together. then that means that S will be theta over 2 pi times 2 pi r, or theta r. We know that the arc length on a circle is simply the angle times the radius. Oh, that's why when I go all the way around, it's 2 pi times r. That's an easy way to remember it. Okay, why do I need that? Because I need that to be able to figure out, I know that opening is delta theta, but I need the length. I don't need just the opening, I actually need the length of that thing. So if I find the lengths of those things, I'm running out of room here. Okay, so I'm going to have, I've already got that guy, and I've got the two different lengths. So I have three lengths here. One of them is going to be, well, obviously the delta phi. Okay, I'm going to have I'm going to have a rho sine phi. Rho I sine phi j, make sure I got that. That width right there is this guy here times that guy, and then I've got the last one. I've got, hold on, I've got the rho, oh, there it is. Got rho delta phi j, and then I've got the delta theta k. Looks kind of ugly. This would be the volume, I'll call it ijk. Kind of ugly looking. Let me rewrite it as. It's pretty terrible looking. That's the magic piece. When we did this with polar, we got delta theta. Okay, if you go back and look at your notes, we derived it geometrically and we found that was the area of our piece. R delta theta. The volume of this coring is rho squared sine, sorry, that. See, I got to catch myself with my sloppy phis. Rho squared sine phi turns out to be the additional component that we would do when we switch it over. The rho squared sine phi acts the same way the r does in the r dr d theta. Now I'm going to also derive that from a completely different point of view next day. The one thing I don't like is the fact that I can't draw a very good picture, but you know, we can live with that. So here's the way it looks then, if I'm actually doing the problem. I've got a triple integral over the volume of f of x, y, z, dv. Okay. By the way, f of x, y, z can be 1. You know, I don't actually have to have anything there. But when I switch it to spherical, this is going to become f of rho phi theta based on these substitutions. No big deal. We did the same thing with polar. We did the same thing with spherical. But what's the big difference? I'm going to have a rho squared sine phi. Generally, you're going to go d rho, d phi, d theta. That's generally going to be your limits because the rho is usually going to be a function of phi or theta, somehow or another, or it can be constant. But theta, like before, is probably going to go all the way around. Now, here's where we get in a little bit of trouble. Okay. I'm going to bring the floor really high up in the air, okay? So theta is this angle here. That hasn't changed. Theta can go how far?
2 pi.
Go 0 to 2 pi. That doesn't change. Theta is still going to range from 0 to 2 pi. Phi is the angle I'm making with the positive z-axis. Pretend our xy plane's up here. 0 to pi. So what, can't it go that way? No. I'm a point here. Since theta goes all the way around, oh, as phi, you said, but what if I want my phi on the other side? Well, theta is how you get to the other side. You don't go this way. Phi is only going to go from straight up to straight down. Remember, phi is the angle made with the z-axis. You can't, if I asked you to measure an angle, to physically measure an angle, there's an absolute that you learned as babies in math. If you're measuring an angle, I'm not talking motion, I'm talking a static angle. People confuse. You know, when you're doing your skateboard tricks and you did a 720, that means you did 2 full circles. That's not measuring an angle. That's motion. That's complete. They're not even from the same universe. I want you to measure this angle. You have 2 possibilities. Do you measure it this way or do you measure it this way? Which one do I measure? It's not a choice. The measurement of an angle is a value between 0 and 180 degrees. That's it. An angle cannot exceed 180 degrees. That makes no sense. That's an impossible, it means you measured the wrong part. If I have a line, the angle measures 180. Everything else is less. An angle, not motion, don't confuse motion. So if I said, Griffin, I want you to go open the door and open it to about a 240 degree angle. That would be a confusing instruction, wouldn't it? Because you're like, how do I, wait a minute. I can go from 0 to 180, but I can't go a larger angle because you're measuring it against something else. So with this understood, oh, if I'm measuring against the z-axis, 180 degrees is about the most I could get, and that would be straight down. So phi, and of course we use radians, phi can only range from 0 to pi. That's, in other words, it isn't necessarily going to be 0 to pi, it might be smaller, but that's the maximum. Then what's rho? Well, that's going to be from the center to the outer edge. That's going to feel very much like the R does. Okay, before I go on, any questions so far? This is brand new unexplored territory. It's terrifying, but when you actually have cause to use this, it's because it makes everything a lot easier.
Are you saying that V equals that, or?
Am I saying phi equals what?
So under the triple integral, you have V. Like what is the position of the f of phi for all the angles and stuff?
Are you talking about this?
No, yeah, that.
Oh, I'm saying when I convert it to polar, I'm changing the x, y, z and the rhos, phis, and thetas based on the substitutions we just did. That was what I said. That is never going to be terribly complicated because once again, go back to polar for a moment. You change it to polar when the region and or the integrand suggested it. So you saw x squared plus y squared. So you're going, I'm going polar. I see an x to the 4th power. I'm not thinking polar. I see e to the x. I'm not thinking polar. Right? You go polar because, oh, I saw x squared plus y squareds. Maybe under a square root or something, or raised to a large power. Oh, okay, so I'm seeing x squared plus y squared plus z squareds. Or I'm seeing things that make sense, or I'm integrating over a sphere. One or the other or both. So let's start with a really simple problem. Let's use spherical coordinates. Let's find the volume of in English, let's find the volume of a sphere of radius a centered at
0.
the origin. Agreed? Now, well, we already know how to do this. We know how to do this because somebody told us a formula when we were kids. Now, in Calc 1, when we learned how to do volumes by rotations, I set up the semicircle, then I rotate it to create the sphere, and then I use that one with the slices and all that. It's really cool. It's a little complicated on the setup, but it's actually a really cool problem. You guys remember that? And it's a single integral because that's all you can do in Calc 1. No, I actually want to do this as a triple integral. Say, why? Because in Calc 1, when we did volumes by rotation, you were able to find the volume of that sphere. Oh, by the way, my sphere isn't just a sphere, it's a medicine ball. Anybody know what a medicine ball is? It's a ball filled with stuff. Could be Jell-O, could be fruit cocktail, could be sand. But one thing that's true about my medicine ball, it is not uniform density. So I want you to find the mass of my medicine ball. You know the volume of my medicine ball, that's easy. I want the mass of my medicine ball. That's impossible without what we're about to do. Can't even do that with polar or cylindrical. You have to use spherical. So let's figure out how to do this as a volume problem. Then if I actually wanted to do it as a mass problem, like a medicine ball, all I have to do is insert the density into my integrand that already had everything else anyway. So when I do this, this is the usual order, unless there's some way that this is defined to make you want to switch. When we just did cylindrical, we generally went dz, dr, d theta, and I'd be hard-pressed to come up with an example where you would deviate from that. Same thing here. You'd be hard-pressed to come up with an example where you deviate. Now, this is a sphere, so that means all of these limits of integration are actually going to be constant. Because rho is going to go from the center of the sphere to the outer edge. And by the way, this is exactly the same thing, isn't it? Just like with a circle, you can say r equals a constant. A sphere centered at the origin, you can say rho equals a constant. Because the left side is rho squared equals a squared, so therefore rho must equal a. Isn't that nice? I mean, it's like, oh, okay, that made it easy. So is it safe to say that rho is bounded by 0 to a? Phi, in this case, is bounded 0 to pi, and theta, in this case, is clearly 0 to 2 pi. I want that to be obvious, because that makes it really easy now to set up my integral. So 0 to a, 0 to pi, 0 to 2 pi. Well, boy, this is a simple enough integral. Well, there is one piece that I need also. What goes here? Rho squared sine phi. I need that piece. And I'm going to demonstrate. All right, so I do my first integration. I'm integrating rho, so 1/3 rho cubed sine phi from 0 to a d phi d theta. Keeping in mind that you're making your phis and your thetas different. All right, so when I evaluate this, what do I get? So I get 1/3 a cubed, which is a constant, by the way. Okay, now let's integrate the sine term. What's the antiderivative of sine?
Negative cosine.
Negative cosine. So cosine of pi is -1, right? So I have cosine of pi minus cosine of 0, so that's -1 minus 1. That's -2. Oh, but I already had a negative. So that's a good thing. So now I am positive 2/3 a cubed d theta. Constant integrand. Can I just multiply by 2 pi? Huh. Well, that's kind of interesting. The volume of a sphere of radius A we just derived as 4/3 pi a cubed. Right, crowd goes wild, confetti everywhere? Or is it more of a, didn't screw it up? Yeah, a little of both. But would you say any part of this was challenging? No, this was really easy. Why? Because your limits of integration were constants. That's what makes things easy. You hate it when your limits are other functions, because then it means every time you integrate, it gets more complicated, not less complicated. Wow, that was cool. Now, what if I said, okay, now it's the medicine ball. I'm going to give you a density. Where would the density go? Right next to this guy as a multiplier. Okay?
What would a problem look like where your phi isn't from 0 to pi?
Where my feet, how about hemisphere? By the way, that is a great question, because we're going to do that in a moment. I want the volume of the hemisphere. So phi is going from 0 to pi over 2. Now think about that logically. If phi goes from 0 to pi over 2, what would change? Oh, it would be 0 minus 1 instead of -1 minus 1. So 0 minus 1 is only half as big. Does everyone see the ripple effect? Then at the next stage, I'd have a 1/3 rather than a 2/3, and I'd get half my answer. So if I'm going less than the full sphere, that's what it is. So we're going to do that one in a moment. Okay? Good question. Anybody else? All right. I now want to calculate the volume of my ice cream cone. I'll do it over here. Now this one is a little bit more complicated setup. And it's not as intuitively obvious. All right, so I want to do I am bounded by excuse me. Actually. If I do x squared plus y squared equals z squared, that's a cone. But that's both the top and bottom cone. If I do z equals the positive square root, then it's only the top cone. Lest you forget, z equals the square root of x squared plus y squared is just a simple circular cone. Literally the cone we use in conic sections. It's that cone. I just want that cone. So I want this. It would be that if I did it as, did everybody follow? Because z would be a plus or minus. I just want to do this piece. Right, I want all of this volume. Well, that's not so bad. My row is still going to go from here to outer edge. I'm not cutting it off with a flat top. I'm cutting it off with the edge of the sphere. My theta is still going to go from 0 to 2 pi, but my phi will clearly not be 0 to pi. It's only going to be from 0 to here. Does everybody get that? Oh, so what is that? Now this is why I said it's a little bit trickier. I'll explain that. Okay, so we are in the first octant, but the sphere is going all the way around us. So the ice cream cone is coming out like this, right? And I see the dome on top. How do I calculate that angle? Well, actually, that is not complicated, and I'm going to tell you why it's not complicated. Because the coefficients on the x and y are both 1s, this is easy. If I put coefficients other than 1, this would be really difficult, really complicated. Okay? Here's why this is not difficult. In the x, let's start in the xz plane. That means y is 0. In the xz plane, what do you have? In the xz plane, you have z equals the square root of x squared, which is the absolute value of x. So isn't this line z equal x and this line z equal negative x? Okay. By the way, what is this angle?
45 degrees.
It's a 45-degree angle, isn't it? How do you know that? Because your slope is 1. In the yz plane, isn't it the exact same picture? It's a 45-degree angle because your slope is 1. So what are your phi? What's your phi range here? Pi over 4. This is why this is easy. If I put a coefficient here, now these lines are not z equal plus or minus x, they're z equal plus or minus 2x or a half x or 3x. So what's the difference? How do you calculate? Technically, we calculate this angle. This is phi, but usually we're thinking of this angle. That's 45 degrees. It's the inverse tangent of 1. Remember, the slope of the line is equal to the tangent of the angle. Oh, so if I make that slope anything other than 1, then I'm taking the inverse tangent of a ratio that's not 1, which means my angle is not 45 degrees anymore, which means my limits of integration wouldn't be 0 to pi over 4. They'd be 0 to inverse tangent of some number. Yuck. And that would carry all the way through to your final answer. So your final answer would be yucky. Does everybody agree that would be yucky? So that's a problem that we generally avoid, not because you can't do it, but you can't answer it cleanly. You're having you know, sines and cosines of inverse tangents of ratios. But we're technically doing the inverse tangent of 1, which is pi over 4. Okay? Because the coefficients were both 1s. If either one of them was not a 1, this becomes very, very complicated. In fact, if they were different coefficients, it would be nightmarish. It would be really, really hard to do. So we're not doing that problem. So when I set up this problem, tell me, what's different? Almost everything's the same. Almost everything's the same. How's it different? That's it. That's the only difference now. I'm not going all the way, I'm only going 0 to pi over 4. Now, common sense would say, well then shouldn't my answer be like a fourth as big? It doesn't really work that way though. Because think of it this way, I have a sphere and I'm taking a core out of the sphere. That ice cream cone's probably a lot less than a fourth of the sphere, isn't it? I mean, I could probably come up with a lot of ice cream cones that I could shove into that sphere. So, let's do this problem. Well, actually, let me make it really easy on myself. I'm lazy. Is it legal to do this? Sure. It changes here. You agree? So now what have I got? I've got negative a third a cubed times, what is the cosine of pi over 4?
Root 2 over 2.
Root 2 over 2. Minus the cosine of 0. Root 2 over 2 minus 1 is negative. I have a negative here. That's a good thing. I did everything right and my final answer was negative. Did I do everything right? No. I evaluated backwards, or I forgot the antiderivative at a negative. If I get a negative answer, I made a mistake somewhere. I'm finding volume. Now, don't do what a lot of people do. Oh, I got a negative answer, I'll just make it positive. The error might be somewhere else. No, if you have a negative answer, you have an error. Go back and fix it. Don't just fudge it and make it work. That's a worse error, by the way. Okay, so that's kind of ugly, but wait a minute. That's a constant. It is a constant, right? So can I say the answer is just 2 pi times all of this? Yeah, do you like that form of an answer? It is correct. Do you like the form? No, you hate it. I can go way beyond. I can do better. Well, first of all, I don't like any negative coefficients and fractions. Well, the 1/3 a cubed. What if I wrote it like this? If I did that, well, if I distribute the negative, then these swap. And if I multiply that by 2 pi, this would become what? 2 minus root 2 pi. It's still ugly. But it's well, less ugly. Do you agree? We agree that it's still ugly though, right? We all agree it's ugly? But I can deal with that. I can deal with that. Wow, it's not a pretty answer. Now, if I calculate this versus the other one, how much is this compared to the other one? Well, one way of doing it is to just take a ratio. Let me go over here. Because we're not done. We're still working on this shape. I love this shape because there's so many questions I can ask that are different questions that help you see all the ways of setting it up. If I said, what fraction of the sphere did I actually just come up with? Aren't I just taking this ratio? Well, do I get lots of canceling? I don't know, I think we just got lots of canceling. So what is that ratio? What's left? 2 minus root 2 over 4. That's not a fourth. Give me a decimal value for that, will you? 0.15. approximately 0.15. A fourth would be 0.25, so this is significantly less than a quarter. It's a little more than an eighth, but it's a lot less than a quarter, isn't it? Common sense, would people say, oh, it's about a quarter because, you know, of my angles. Well, that would be true in 2 dimensions. If I thought of the cone, you know, being the triangular portion, saying what fraction of the area on the XY plane, it would have been a fourth of the area. But that doesn't work in 3D, does it? Oh, okay. Now, next question I have. Now I do want to keep going. And I want that volume. I affectionately call this the bead. It's a lousy to, you have an orange. And you just took a core of the orange, like an ice cream cone, and then you took a core at the other end. So it's not really a bead. I think of a bead as a big hole down the middle. But I took a core at one end, a core at the other end. How much of the orange is still left over?
The original orange minus that.
Yeah, so I want to set up that problem from beginning to end, and then I want to compare them. Because this is my favorite question to ask because there's so many things I could ask. I could say, what's the volume of one of the ice cream cones? Or I could say, what's the volume of 2 of the ice cream cones? I could say, what's the volume of the outer portion, you know, with both cones removed or one cone removed? It really depends on what do you ask first. If I had started by asking you for this outer portion, you'd be wasting your time finding the cone first and then subtracting it from the whole. By the way, would that be correct? Yes, but it's extra work. So I want to show you how to calculate everything directly and then show you that everything actually does match up beautifully. So now let's find that bead, if we will. So now what's different? Well, we agreed this was 0 to pi over 4. Therefore, what should this be?
0 to 5 or 3 pi over 4 minus
You guys are thinking too much.
pi over 4 negative 5. There we go.
Well, horizontal would be pi over 2. 0, pi over 4, pi over 2,
3 pi over 4.
3 pi over 4, pi. So what are my limits, you think?
3 pi over 4.
We're throwing out right numbers, but we haven't given a right answer yet.
3 pi over 4 to pi over 4?
Well, then you're going to get a negative answer, so that won't work.
Or pi over 4 to 3 pi over 4?
How about pi over 4 to 3 pi over 4? Kind of has to be increasing, otherwise you're going to get a negative answer. So you asked it earlier, how do you get a negative answer? By going backwards. So pi over 4 to 3 pi over 4. What am I excluding? I'm excluding the cone on top, and I'm excluding the cone on bottom. Well, if the cone on top was 0 to pi over 4, then shouldn't the cone on bottom be 3 pi over 4 to pi? Oh, okay, so I want the in between. This should make sense. Okay? So far, so good? Let's do this problem. Now, I'm being lazy because we've already done all this. All right, now you got to pick it up right about here. Okay, so cosine of 3 pi over 4.
Over 2.
Negative root 2.
How about negative root 2 over 2? Ah. Minus cosine of pi over 4. What's negative root 2 over 2 minus root 2 over 2?
Root 2.
That's just negative root 2, isn't it? Huh. Well, this one's actually a little easier than the other one, then, isn't it? So now what have I got? I've got 0 to 2 pi of negative root 2. So 1/3 a cubed root 2. Oh, okay. Wait, that's constant. So can I say my final answer is 2 pi times this? Now, it does not matter what order you put things. Most of you probably say, you know, I can put the pi last. Or do I put the pi first? Or do I put the pi in the middle? Or do I put the a cubed last? Yes. All of those are yes. Does it really matter what order you put things in? No. Why? Because they're all constants. They're all constants. A is a number. You're not even going to see that in your final answer. If I gave you that, A was 6. Okay, you now have 6 cubed. You're not going to worry about that. I don't care where you put things, but I have a 2, I have a 1/3, I have a root 2. I probably should put those together. So maybe 2/3 or 2 root 2 over 3 pi a cubed. I don't know, maybe that. Just something that looks a little prettier. Now that's the volume of my bead, quote unquote. I think I did it right. You're doing an assignment, maybe you're doing this in a physics class, and you want to know that you did it right. Because if I have the wrong volume, then any follow-up questions will be incorrect. Well, can't I check it the other way? I wanted you to find the density, or excuse me, the mass of this thing. Oh, doing the other stuff won't work. I need to set up this integral correctly. Well, if I know that I did the volume correctly, now if I inserted a density, can I at least trust that I'm going to get that part correct? If you got the volume correct, you have to have faith that you're going to do the rest of it correctly, because you set it up correctly, you integrate correctly. Can I know that this is correct based on my prior answers? This is the question one of you had earlier. Yeah, this is where I'm going to do the cross check. All right, so what did we say? Volume of the sphere, 4/3 pi a cubed. Volume of the ice cream cone, I'll just call it ice. What was that? That was kind of ugly. I erased it.
1/3 a cubed, or a cubed, parentheses 2 minus root 2, pi.
That's horrible. So now, the volume of the, I'll call it the bead. I actually can't think of another term for that. It's not a bead, but it's kind of like a bead, and I hollowed out part of the inside. What should it be? How do I get the volume of the bead from those first two?
Oh, minus 2,
Minus
2.
2 of these. Does everybody follow that? Let's do that and see what we get. It's kind of hideous looking, I get you. So I've got, can I factor anything out of this? How about if I factor out, I'm going to factor out 1/3 a cubed pi. I'm lazy. I don't want to do it. Let me do that and just work with what's left. So what's left then? Well, actually, heck, let's do 2/3. Sorry. I forgot that 2 there. If I factor out 2/3 a pi, I have 2. That's all that's left. And on the other side, what would I have? Just that. Oh. You like that? This is proper lassitude on display here. Well, that makes it a lot easier, doesn't it? So what's this answer? 2/3 a cubed pi times root 2. Same thing? Is this the same answer over here? Some of you are shaking your head. No, the same thing, just rearranged. Oh, so what does that mean? That means we did this one correctly. So there's multiple questions that could be asked on this exact same problem. I love using this problem because the setups are not terrible. I mean, what did we change? We only changed the phi limits each time. So we have a sphere. We have one piece of the cone, or we have 2 pieces of the cone. We have the outer bead. We could have the outer bead only excluding the first cone. Regardless of which one I asked you, you would want to set that one up directly. Now, I'll ask a question like this, and I'll have people do everything but. They'll do all of this. And I'm like, no, do it directly. It's faster. It's just flat out easier every time. Now, one more. I only want to remove the core. I want to take this cone out, and I want everything else. Now what would my setup be? Pi over 4 to pi, because I'm only excluding the 0 to pi over 4, and now I would go pi over 4 all the way to pi. Now I said you could do this one using cylindrical coordinates. You could. It's not wrong. You could do it using cylindrical coordinates. My theta would clearly go from 0 to 2 pi, but the problem is the r is not going to have constant limits. Okay? R won't have constant limits. R is the part on the XY plane. Ooh. So, and then the Z, okay, well, won't the Z? No. Z will be between here and here. So Z is between function and function, and I have to rewrite everything. Well, here's one of my functions, and the other one would be the square root of a squared minus x squared minus y squared under the root. Do you see why I don't think you want to go that route? You can. You can correctly set that one up, and you might even be able to successfully integrate it. Man, it would be a lot harder. And trying to figure out your limits of integration. Now, I'm going to give you a simple absolute. If spherical works, you can do it in cylindrical. It's more work, but you can. If it's cylindrical in nature, you cannot do it in spherical. Not possible. Let's just take the simple can. Rho will not have constant limits. Phi will not have constant limits. They would have functional limits which are really, really difficult to even find, and now your integrand you may not actually be able to integrate because you have to replace now x squared, y squared, z squared. So if you have something that is cylindrical in nature, you can't switch it to spherical. If you have something that's spherical in nature, you can do it cylindrical, but cylindrical is a lot more work. Now, how do you decide? Well, how do you decide polar in general? Because your region in the xy plane was circular, or your integrand suggested it, or probably more often than not, both. How do you decide cylindrical? Well, it's three-dimensional polar. Same thing. My z has nice limits. I'm bounded by nice things, and I'm still circular in the xy plane. Okay. How do you decide spherical? I'm bounded by a sphere. Or my integrand is x squared plus y squared plus z squared, maybe to some crazy power. Probably more likely you're bound by a sphere, though. Okay? Question. That's it. So that's cylindrical and spherical. These are tools. These are not dominant things. Being able to do everything in XYZ world is still, the main thing. And being able to switch to polar, we've already seen, is extremely useful. The quiz you just turned in today, for some reason, there's this misconception that every time you do surface area, it always switches to polar. Well, the first problem, certainly polar made perfect sense, didn't it? Because, in fact, I just did that problem today, right? This guy here, surface area, you switch it to polar, piece of cake. But the second problem, there's nothing circular about your region and nothing circular about your integrand, so switching that one to polar would be really difficult. Not impossible, but really difficult. If I leave it rectangular, I get a nice happy integration. It doesn't require anything tricky. So the first problem, absolutely, you go in polar, but the second one, you're leaving rectangular. I did that on purpose to show you, no, it's not always polar. Now, what about the last one? That's the one that gets people a lot of times. What am I doing? I have a sphere, and I'm cutting it off. So I'm taking the rim, I don't even know what you describe that shape, but that shell, if it helps, think of it this way. I have the top half of the sphere, and then I'm shaving off the contact lens on the ultimate top part of the sphere. So it's the ring that's left over. Does that help? That's what you're finding. And it turns out that one shouldn't have been terrible, particularly because I also used numbers that worked out really, really nicely in that one. So I'd be interested to see how many people, got that one right. I always love it when you get stuff like that right, because it kind of confirms that you understand what the heck's going on. All right, so where we are now, we have one more day of integration stuff. One more day, that's it. On Monday, we finish everything that is this multiple integration, multiple dimensions. After that, we move on to what's called vector calculus, which is confusing because you say, what did we do the first month? We did the calculus of vectors, right? Motion, simple stuff. The vector calculus is a little more complicated in terms of the understanding. So that's where we are. And so in terms of where are we content-wise, we're actually halfway to the next test already. Sounds kind of crazy. But the next test is about 1 million years away. It's just way after after Thanksgiving and all that. So we got a lot of time to prepare. The next day, I just want to give you a fair warning. We are going to come up, it's basically theory. We're going to be doing algebraic problems because we're going to do integrals. But the theory is we are going to go back and justify every substitution you ever did in calculus. What justifies a U substitution? What justifies a trig substitution? What justifies a polar substitution? Heck, what justifies a spherical substitution? Well, I got the right answer. Doesn't that always work? The end justifies the means? Isn't that the way, isn't how people justify wars? At the end? No, the end does not justify the means mathematically. We never were ready for the theory that explains where everything came from. We're going to do that next day, and it's actually really crazy cool. And it's the only part of the course that actually uses linear algebra. So those in linear algebra, it actually uses matrix theory. It's not possible to do things without a matrix. Now, if you're not in linear algebra, you don't have to understand the matrix theory. I'm going to walk you through the parts you need to do to understand it. And then we're going to work with problems that are not terribly complicated. But it would be good for you to understand, oh, this is where it came from. I don't have to derive it myself. How often did you have to rederive the derivative of sinus, cosine using limits and all that? No, you saw it, you said, okay, I understand it, and you moved on. You've long since forgotten how it was done, but you saw it done, it was done correctly, you believed it, and that's all you needed to do, you believed it. I don't need you to derive what we're going to do, I need you to see where it came from, because from a mathematical standpoint, it can only get bigger and scarier if we understand where things come from. Then we understand down the road, when we're shown things in other classes, okay, I understand where it came from. I don't have to derive it myself, but I do understand where it came from, and it's not just do this. See, unfortunately, some of the textbooks, it's just do this. There is no textbook. There is no calculus book written that thoroughly explains what we're going to do because the authors don't know. They know what the right thing is to do. They're not going to be able to tell you why. Okay? Let me go and stop. Let me do the roll.